Um, my name is Aria, and I'm going to talk about piezoelectric materials. Uh, First of all, I would like to know whether is there any guitar player here? Somebody who knows, or other
I can
music
play a
instrument?
little bit, but not much.
Not in concert or something.
I can play maybe one or two songs at best.
Well, I'm sure all of you have seen that appliance, the microphone which attach on the musical instrument to amplify the voice, the sound. And you might know, you might guess that I am going to say that this microphone has piezoelectric material. And now I would like to talk a little about it. And actually, piezoelectric materials are classified in dielectric material, and I'm going to describe it later. But they are actually defaults that are aligned very permanently. They don't change. And there are two kind of effects that we can see in piezoelectric material. The direct, which is when we apply pressure or, for example, a tension or pressure, we will see that there is a charge on the surface of the material. Here we can see in the picture that with pressing or with tension, we have change in potential if we connect it to the voltmeter. And inverse effect is that if we apply potential to the material, we also can see the change in the size of the material. For example, we can see contraction or expansion. Here we have connected the piezoelectric material to a battery, and we can see that by applying potential, we have expansion or contraction in the material. And this is what helps to, in microphones or other appliance, to have the use we are looking for. Here is also shown how it works. When we press the piezoelectric material, both sides of the material will have charge, and we can measure it actually. Well, the history of piezoelectric, the word has come from ancient Greek and Pisian, which means press or squeeze. And first this effect was seen by Pierre and Jacques Curie in 1880s. And now I would like to talk a little about the mechanism of these materials. As I said before, there are dipoles in the material. Dipoles means that the molecules of the material have different parts, one positive, one negative. For example, we can see even in water. I think maybe you have covered it in high school science, that for example, water has the part of oxygen and two hydrogen, and oxygen has the negative charge regarding respecting to hydrogen atoms. When we have such arrangements, when we have this in some materials which we call them piezoelectric, and when we put pressure on them, these dipoles will get closer together. Comparing to here, we can see that by pressure these dipoles get closer, so we will have a charge on both sides of the material, and this is what we are calculating by volume voltmeter. On the other side, if we connect it to a battery, we will have positive charge and negative charge both sides of this, and this charge causes that these dipoles get far from each other. Therefore, we can see that the material expands actually. And there is a very simple equation for it. We can calculate the amount of displacement. For example, if the thickness, the original thickness of the material was T, and then we apply for example, a voltage over it, we have the voltage, we have the thickness, and K is the ferroelectric coefficient. It's a material property. For every material we have the number. And by this equation we can understand how much the material will expand or contract. Now I'm going to talk about some types of piezoelectric materials. We have it in nature, and also we have it artificially. For example, beryllium, cane, sugar, quartz, and dry bone. Or artificial ones are like barium titanite, lead titanite, or lead zirconate titanite, which is very famous in this category. And the process that we make them is simply we mix the two mixed components in a specific proportions, and then add binder to them, and then make a heat treatment over it. There is a process of heat treatment, firing, and then we can shape it to the form we want. Now, as I mentioned before, there are many applications for it. So one of them was microphone. We can see here how it works. This is a piezoelectric we have. By vibrations that it takes from the instrument, it will contract or expand, and this contraction or expansion makes electric charge. Another application is in inkjet cartridges. There is also a piezoelectric disc, and with applying voltage, it will contract or expand, and this expansion puts a pressure on this metal sheet, and it causes that a droplet of ink comes out from nozzle. Another one is whenever you are pressing the gas pedal in your machine, in your automobile, there are some piezoelectric materials under your feet, which they determine the amount of the fuel that goes to the cylinder. There are some other applications, sonic and ultrasonic. For example, we can understand the flaws in the cast metals by using this property of piezoelectric materials. And now I would like to summarize what I said. Piezoelectric materials can convert electric energy to mechanical energy and vice versa. And also they could be prepared in natural, or could be prepared artificial. And the displacement or the voltage needed could be calculated by displacement, could be called ferroelectric coefficient multiplied voltage divided by thickness. And some applications of it are in microphones, ultrasonic, inkjet printers, and automobile accelerator system. So if there is any question, I'm happy to hear.
So the whole thing of it is that the material, like with the guitar, it like senses vibrations and then transfers that into like an electrical energy for us to like.
That it changes to electrical energy, and there is another semiconductors that amplify it. It just change the vibration to the electric